Well, everyone, welcome to Math 221. Um, we're going to be taking a look this quarter at calculus. And depending on the circle you run in, calculus is either famous or infamous or a little bit of both, which I believe is the most common one. Um, and before we get started with some of our preliminaries, I want to sort of ask the question of why calculus, okay? Um, and there's sort of a number of reasons. One, not to wax too philosophical about it, but it is one of the um, most important and greatest discoveries of modern mathematics and modern science. Um, but sort of more than that, calculus is concerned with the nature of change and how we can measure change. Um, and so even if you don't find yourself using the calculations that we will learn, um, what it will do is it will develop this insight into it, and that can serve you going forward, right? And then one other reason, um, which is sort of one of the reasons that we teach math in general, is that you can sort of think of math as weight training for the mind, right? It is a way to um, practice and develop logical reasoning skills, right? Especially in the sense of calculus, where we're looking at these in the context of understanding how things change, right? And so, training up those skills that will absolutely pay off, even if you don't end up, using a derivative in your daily life. Understanding like how these things work, that absolutely will pay off. Okay. Um, but in order to jump into calculus, first we need to look at some preliminaries. Okay. And here is what I'm going to assume that you know. Okay, so if a concept comes up here and you're not very familiar with it, there's good review in the book, um, and there's tons of educational resources all over the internet. You can look there. You're also more than welcome to drop by my office hours and ask questions about them. Okay, so I'm assuming you're comfortable working um, with intervals and interval notation. Right? So understanding, right, what the set, A, B is, where we have a hard bracket here and a soft bracket here. Um, maybe the interval negative infinity to A, things like this, right? I'm going to assume that you're comfortable with that. Um, I'm also going to assume that you're comfortable with exponent laws. Maybe things like a to the n, a to the m, and that being equal to the a m plus n. Um, things like a to the n all to the m being a to the n times m, things like that. Okay. Um, I'm going to assume that you're comfortable with factoring, things like factoring binomials, your perfect squares, your perfect cubes, things, that generally fall in line of factoring. Okay. And then the final one that we will be dealing with a lot um, are just working. I'm going to assume that you're comfortable uh, working with rational expressions. Okay. Um, right. Taking a look at something like x plus 2 over x plus 1 plus maybe x plus 3 over x minus 1. I'm going to assume that you're comfortable transforming this into something like, looks like it's going to be 2x squared plus 5x plus 1 over x squared minus 1, right? Where we find that by, getting a common denominator here and here, multiplying this guy by x plus 1 over x plus 1, this one by x minus 1 over x minus 1, getting our common denominator, expanding the products you get up here, and then adding them together, okay? And the other big thing that we're going to be working with a lot with these rational expressions is rationalizing our numerator and rationalizing our denominator, okay? So say you have something like 1 over 1 plus the square root of x, right? More often than not, when we get some sort of square root in the denominator, we don't want it in the denominator, we want it in the numerator. A little bit less often, but this one does happen. You might have a rational expression or you might have, something with the square root in the numerator that you don't want there, okay? So we'll do an example of each of those, right? If we're looking to rationalize this denominator, well, then we need to multiply by something that will make it go away. In this case, 1 minus the square root of x, right? This red thing is just a big fancy 1. We end up with 1 over the square root of x. This is the expanded form of a difference of squares, right? So we're going to get this guy squared minus that guy squared. So it looks like we're going to end up with 1 minus x, okay? Alternatively, say we have something like, for instance, the square root of 1 plus h minus 1 over h. In a few weeks, it's incredibly likely that we'll meet this guy again. And for when we get there, we do want to be able to rationalize this numerator, okay? As strange as it may seem, okay? So when we want to do this, we need to multiply by something that will make the numerator, or make this square root in the numerator go away. And we can do this by multiplying by 1 plus h plus 1, right? Its conjugate, over 1 plus h plus 1, okay? When we carry out this multiplication here, we're going to get 1 plus h square rooted and then squared, right? So that's just going to be 1 plus h, and then minus this times this, which is just 1, okay? Then I'm not actually going to carry out the multiplication on the bottom, because if you'll notice, when we have 1 plus h plus 1, on the top we have a factor of h, and then on the bottom we have h times this guy right here. And then these cancel to give us a 1, and we're left with 1 over 1 plus h plus 1, okay? And so we've taken this guy and we've found an equivalent expression, right? We've only ever multiplied by 1, such that our factor with our square root is now on the bottom, okay? And why we might want to do something like that is, I think, going to be better motivated well, once we actually understand why we would get an expression like that in the first place, and unfortunately we'll have to wait a little bit for that, okay? The final thing that I'm going to assume that you're comfortable with is just generally working with inequalities, okay? So we're solving equations of various kinds. That's all over 118. And then every once in a while in there, rather than solving, x squared plus 2x minus 8 equals 0, you're looking for where x squared plus 2x minus 8 is less than 0 or is greater than 0, and all of that. Okay, so with these assumptions out of the way, we're going to take a quick look at sort of our arena of calculus, sort of where we're going to be doing it, and then we'll take a look at lines, okay? So we're going to be doing calculus in the Cartesian plane, okay? We're going to be looking at functions from the real numbers to the real numbers, and we can draw out all of those on the Cartesian plane, okay? And my guess would be, since you're in calculus, you're familiar with the Cartesian plane, right? You have your x-axis here, you have your y-axis here, right? You know, sometimes these are just arbitrary copies of the real number line. Sometimes there's something more interesting. You might have, you know, time here and profit here. You might have distance traveled on a road trip increasing to the right, and depending on how you do on road trips, sanity either increasing or decreasing vertically, okay? And I'm going to assume that you're fairly comfortable with, you know, plotting points in here. You know, you have an idea of the large scale structure of this, right? If I gave you a point, you would know that depending on the sign of the numbers, well, that can tell us which quadrant we're in, okay? Traditionally, these are numbered like this: 1, 2, 3, 4. They got these numbers because for some reason in math, everything is done counterclockwise. And as far as why they're always written in Roman numerals, who's to say, okay? A thing that will be very useful for us throughout the course of the quarter is our distance formula, okay? So say we have 2 points, right? Say we have this guy right here. We'll say he has coordinates x1, y1. And we have, let's grab this color, x2, y2, okay? And we want to find the length of this line right here, okay? Well, the distance formula comes from this guy, right? So the distance between the point x1, y1 and the point x2, y2, well, it's nothing but the square root of the sum of the squares of the differences, right? It's kind of a mouthful, but that's all it is, right? It's the square root of the sum of the squares of the difference, right? And where this comes from, right? Let's imagine for a second we drew this line here and this line here, right? Well, now we have a nice little right triangle, right? The length of this piece here is going to be y2 minus y1, right? Well, the absolute value of it, right? And the length here is going to be x2 minus x1, again, in absolute values, okay? And, well, our Pythagorean theorem says that this squared plus this squared equals this squared. So if we want to solve for this, we just take square roots, and we get the square root of the sum of the squares of the differences, okay? A thing that I want you to sort of pause right now really quick and think about, you know, sort of pause and ponder. I claim that you can switch these around no problem, right? The distance from, say, A to B should be exactly the same as the distance from B to A, okay? But we're subtracting here, right? And subtraction doesn't go either way, right? 5 minus 2 is not 2 minus 5. So pause, think about it, convince yourself. Why can you just switch like this, right? Why does that work? Okay. Like I said right at the beginning, you can sort of think about math sometimes as sort of a you know, mental weightlifting, right? Sort of training your brain and taking time to pause and ponder in situations like this is absolutely always worth it, okay? So the most basic construction on the Cartesian plane is just a point, right? You take the axes and you add a point here, or maybe a point here, right? Going up one level of complexity, you have lines, okay? And calculus is studying functions that think they're lines, okay? And we'll totally firm that up throughout the quarter as far as what that means. Um, but if that's true, right? If you take me at my word that that's a good way to think about calculus, well then before we jump into calculus, it bears for us to take another look at lines just to make sure that we're all on the same page. Okay. So the lines have a single defining property. Okay. And that defining property is their slope, right? Slope is what defines a line, right? Yes, it needs to pass through a point, right? Um, but the slope is the biggest thing that's going to differentiate between different lines, okay? And if you recall, our slope is almost always denoted um, with a lowercase m, okay? And it's delta y over delta x, right? Where this delta represents some finite change, right? So in this case, right, you might pick your 2 points on the line, and then you'd go y2 minus y1 over x2 minus x1, right? This is some measurable change. And if we take a look at, once again, some arbitrary line, say, I don't know, this guy right here, right? If we take some, delta x step, maybe like that, right? And we take some delta y step, maybe like that, you see we're back on the line, okay? And this ratio of delta x, or of delta y over delta x, it's constant throughout the whole line, right? That is why it's our defining property, right? If we take a little tiny step, maybe like that, right? Well, then in this case, go back to your geometry class. These two are similar triangles, right? And we're going to get the same ratio here, okay? So slope is this very, very important concept, right? And just like it's worth having a conceptual understanding of, like where different points are on the Euclidean plane, right? It's worth, having an intuition, right? That if some line slope is positive, then it's going up, right? If some line's slope is negative, then it's going down, right? If some line's slope is 0, then it's going across, right? But then this bears the question, right? What kind of slope does a line like this have, right? Our ideas of positive, negative, and 0 come from this idea right here, right? You'll notice on the positive one, if I step to the right, I step up, right? Right is positive and up is positive, so we're good. For our one with the negative slope, if I step to the right, I step down, so we have a positive and a negative, and so we get a negative slope, right? Here on our no slope one, right, if I step to the right, I don't step up at all, right? So we get 0 over any x1, x2. So we get a 0 slope. But then what happens here, right? Say we pick 2 points, right? Say they're at a comma b and a comma c, right? Well, then my slope of this green line, well, it's going to be b minus c over a minus a. But a minus a is 0, right? And this is a problem, right? Because no matter what math class you're in, you can't divide by zero. It just doesn't work, right? So we say that these vertical lines have no slope, okay? To sidestep the issue of what slope do they have, we say they don't. It's not possible. They don't have a slope. They're vertical. We're dividing by zero. Everything gets bad when you divide by zero, so they don't have a slope, okay? There are a number of common ways for us to write the equation of a line, okay? And we will get very used to this, remember, because calculus is studying functions that think they're lines, okay? And so the equations of these lines are going to be important when we want to do some sort of like, actual analysis of them rather than just, drawing some pictures. So let's take a look at some of the most common ones. Again, you've almost certainly seen all of these before, but it's the first day, so I want to make sure that we're kind of all on the same page, okay? The first one is the point slope form, okay? If we said that the slope is the defining property of a line, okay? Give us some axes. If we said that the slope is the defining property of a line, right? Let's say we have some line with slope of 1/2, okay? Maybe like that. Well, as I drag this line vertically like this, all of these have slope 1/2 as well, right? So in order to get a unique line, we also need to fix a single point. Say we'll fix it here, right? At some, x1, y1, okay? Well, then our equation for the line becomes everything that every point xy that satisfies this equation, right? And this equation comes directly from rearranging this, okay? Once you fix some point xy, you get this, okay? And in this case, in the case of the green line we've drawn, right, that's going to have equation what? Well, it's going to be y minus, looks like our y1 is 2, equals, our slope is 1/2, then we're going to have x minus x1, which is just equal to 1, okay? So one of the complicated things about this is you have to nail down a point, okay? You have to have a single point that's on the line. And often it's handy to, always have a point that it's easy to pick, right? And that's where the slope-intercept form comes in. And the slope-intercept form says, okay, well, the point that I'm going to pick, I just want it to be wherever the line hits my y-axis, right? I want to make x1 0, and then whatever y1 is will automatically become this point right here, okay? And in this case, you can get this from the graph, but I think it's worth, going through the algebra and solving for what our y-intercept ends up being, okay? But when we transform this into point slope form, we'll get y equals 1/2 x plus 3/2, right? And if we were attempting to graph just from this, well, we would know that our line hits the y-axis at 3/2, and it has an overall slope of 1/2. And those two pieces of information uniquely determine our line, okay? And since I realized I forgot to write it, we'll move that down and we'll give the general slope-intercept form is the famous y equals mx plus b, right? M being our slope, once again, b being our y-intercept. And the last form that we'll look at is just called the general form, okay? And the general form looks like ax plus by plus c equals 0, okay? Much of the story of 118 is looking at things and trying to generalize them, okay? And this is about as general as you can get for a line, right? You have some constant a times x plus some constant b times y plus some constant c all by itself, and you have that equaling 0, okay? And what's important to note here is that both a and b can't be 0. A can be 0 or b can be 0, but they can't both be 0, right? Because if both are 0, well, then we get just the equation c equals 0, which is only true if, c equals 0. Otherwise, it's a nonsensical statement, okay? And so this general form, it turns out every equation like this is a line, and every line can be written as an equation like that, okay? We're not going to prove that, but it is interesting to sort of think about how you would go about showing that every line can be written as one of these, and all of these can be written as a line, okay? This is going to wrap up this part of the lecture. Come back for the next part, and we're going to take a look at a formal definition of functions and graphs, and that will wrap up our first lecture. If you missed it in the email that I sent out on Sunday, I'm uploading lectures on Tuesdays and Thursdays, and more often than not, just like this one, they will be broken up into 2 parts, right? So this is lecture 1.1. The second part of Tuesday's lecture is going to be lecture 1.2, right? And then Thursday, I will most likely upload, 2.1, 2.2, etc. Okay? So I'll see you in the next video.